First, we will talk about the third section of the introduction of classical physics before moving on to the realm of ancient science and the first mathematics, as well as the first physics. Concerning measurement, it was by developing theory, for instance, by developing astronomy first for the calendar and secondly for navigation, that the idea of measurement was incorporated into science. It entered in two ways: to regulate customary exchanges, which turned into basically trade and taxation, and to regulate the movements of the heavens insofar as they did or were deemed to influence things on earth. Both, however, come together in the organization of a divinely ruled agricultural state like that of ancient Egypt, for example. The beginning of both is the measure. The next step in science after the counting of individual objects is the counting of repeated standardized objects like units of measure. And now, what is such a unit, and what in the first place did it measure? Even today, if you ask for a measure or a referent or a reference point in a shop and do not specify what you mean, such as a tape measure, you will get a measure of volume. You would mean a basket of some standard dimensions or a jug, say, in which you could measure the two things that really matter to be measured. You measure grain, or you might measure beer. The measure of grain was the basic metron. It was a beginning of all measurement. Length was next measured in places, essential for the measurement of area of land. It was necessary in order to know how much of a field was indeed needed to obtain so much grain of this or that measure. Think of a central organization that requires a tax in order to be levied in so many baskets of grain. The tax collector has to be able to prove that the peasant can produce it, or that the peasant has to prove that he cannot. This is the first stage of measuring the ground. In the language of the Greeks, it was called geometry. Fields were measured for their yield. In China, for instance, the standard land measure is called the mu. But the old mu is not always the same area. It would be a large area where the land was poor and a smaller one where it was rich. And so everywhere the mu was the amount of land that should yield the same number of baskets of rice. The measure of weight came later on for things which could not be reduced to length or volumes, beginning possibly with raw wool or going on to metal, especially precious metals. It depended on the invention of the balance. Measure was introduced everywhere for its utility function, devised ad hoc for every purpose, and only after many centuries integrated into a system like the metric system, for example. The last thing to be measured accurately was the first to be measured at all, and that was time. When people became particular about time, or the measurement of time, or what time is, they were not satisfied with counting days. They wanted subdivisions, and it required a certain amount of astronomy in order to get these equal. They had to set up the post to measure the sun's shadow and marked how it moved, and devise a gnomon and the sundial in order to divide the days into 12 hours corresponding to the 12 months of the year. And so we have gnomon dividing, making subdivisions of measurements from years to days to hours to minutes to seconds and the nanoseconds, etc. Of course, this arrangement by 60s is an example of astronomy imposing itself on common sense. For example, astronomical purposes, this could be divided into 60 smaller parts, the minutes, and each of these into 60 even smaller parts, the second minutes, and so on. Of course, the first countings were digital in tens. Then it was noticed that there were roughly 360 days in a year, and so it was convenient to divide the circle of the heavens into 360 steps and degrees. A degree means a staircase step, a grade. And starting with astronomy, it was convenient to count other things in 60s. The Babylonians, for example, in history counted 60 minus to the shekel or the shekel in their monetary tables. Their economic calculations were made on the basis of astronomical calculations, for which they had already made elaborate tables. The upper and nobler half of mathematics was concerned with the heavens, and the other half was concerned with buying and selling and satisfying tax demands on earth. But both led to the purely technical development of computational methods. We will see how this more clearly then works because it happened to us in our own times. We are very pleased with the wonderful things electronic computers can do, but the people of 5,000 years ago who introduced the sexagesimal system notation found the concept of place enabled them to carry out and tabulate such functions as roots and trigonometrical functions, which went beyond what they could do on the abacus or on their fingers. And for them, it must have been as big a jump in physics and astronomy as the computer is for our own time in the 20th and 21st centuries. These remarks give, in the barest outline, some indication of the motives that led to the first understanding of what we now call the physical nature of the universe and what was long called natural philosophy. This was connected with astrology, which at the time was considered to be terribly important, and however nonsensical it may seem to us now, this was to turn out to be a very happy development. It is a curious thing that since the weather occurred regularly, although people's business affairs did not operate at all regularly, it was believed that they ought to, and that if only they did happen regularly, everything would be right. So you had to fit in with the big machine. You had to find out how the stars were working, and so forth. And you had to find a correlation between the Earth, the microcosm, and the macrocosm, or the large outside world. This essentially was astrology. Most of the physics up to this point, or at least up to the 17th century, was motivated by the ideas of astrology. Much of our work consists of getting rid of or transforming those ideas, and this is in part what we will be talking about in classical physics. Concerning experiments, next I want to deal with what we call the physical method. The physical method, as we know it, begins with observation and goes on to experiment. What is experiment? An experiment, from its name, means an experience that is often referred to as a trial. People are obliged to experiment, to find out by trying things out whether they will work or not. A considerable step toward was taken when it was realized that you did not necessarily have to find this out on the full scale all the time. In early times, for instance, when people were already developing mining, or at least tunnels, they made quite good tunnels, mostly for conveying water. If you are driving a tunnel from two sides of a mountain, you need to know where you are, especially if you have to make a bend in the tunnel. What they did was this. They took strings and stretched them inside the tunnel. They then went out to the field and stretched the same strings at the same angles in the open. They were then able to see how they were going and which way they ought to turn in order to make the two pieces join, down and sideways. This was all done at full scale, and then some bright person thought that you could really reduce the scale to a tenth or so and do it on a piece of paper instead of having to do it in a large field. But in due course, this led to the idea of the plan. The Egyptians and Babylonians, which we will discuss later, in ancient science, made plans of towns, of fortifications, of fields, and other operations. Somewhere or other, I suppose they have been lost by now, but there must have been plans of the pyramids. They must have been drawn out in dimension. We know that because here was a mathematical problem, a piece of mathematics. They desired to build a pyramid so many ells long and so many high. They had to calculate how many stores were required, how many jars of beer and how many loaves of bread to feed the men, supposing the men could do such and such amount of work a day. Those are the Egyptian elementary textbooks of 2000 BCE. They had to work out, and as you know, it takes a lot of thinking out even now, the formula for the volume of a pyramid. But all of these things, all these approaches to the introduction of mathematics, are part of a way of doing big things on a small scale. The fundamental realization was the mathematical realization of what we call the principle of similarity. Of course, as a notion, it is extremely old because it was used not only for objects but for animals and people. In the Old Stone Age, they drew up pictures of animals, usually fairly full scale, and then drew pictures of spears hitting them, and this was the principle of similarity. Later, they would draw the animals quite small. They would draw them and tattoo them on each other, and it helped them in the hunt. Here the idea of a scale came in. A scale, incidentally, is another of these practical things. It means the steps or the ladder. When the Egyptians had to make one of these magnificent large decorations on temples, they drew up a Cartesian net, a piece of graph paper, and they set ordinary workmen to do the work on the large scale. The artist drew the design on a small piece of paper or parchment and gave the coordinates, and then the workmen put it up at a scale 30 times as big. They had no idea of scale, but experiment was the trial. Now, the best example of trial is not in physics, but in chemistry. If you had discovered a mine and found some ore minerals and wanted to know how valuable they were, you could, of course, take the whole pile of ore and extract the gold from it. You would then know how much gold was there, but you would rather like to know beforehand whether it was worth doing so. So you took a little sample and assayed it in a small way. Instead of using a large balance that weighed half a ton, you used a little balance, able to weigh a fraction of pennyweight. There, then, you have the idea that you can get anything or everything to work by doing it in a small way. And by doing it in a small way, you could see what to do in a big way. The controlled experiment came a long time later, and some of the first and best experiments, which we will be discussing, were those made by Galileo Galilei, who discovered the law of falling bodies by experiment, or to be more accurate, what he really did was to discover which of the laws that had seemed to mathematicians to be equally good theoretically, which was one which crude nature actually used. But his experiment on falling bodies was, in a sense, a little too good. What I mean by this is that he said, I have carried out this experiment 100 times and it always gives exactly the same result. He had not been trained in statistics. We would now say that he must have been telling lies. But the point is that by these experiments you interrogated nature, or in the language of the times, you torture nature and force it to reveal its secrets. In a little sense, you do alter things by forcing them to show what they will do under different circumstances, and then, from that point of view, find out their essential nature. Concerning the building of theories, this leads, as it were, to the final aspect of the experiment. Having had the laws out of the experiment, the very simple laws like Boyle's law or Hooke's law, which are straight experimental laws, you want to see what it all means. What is the interpretation? What is the theory of it? How can you really understand it? And this building of theories, of really good theories, logically ought to have come last, but in actuality, historical development, it came first. The first thing was to know the answer. The last thing was to find out if it corresponded to actual nature. The general view was, if it did not correspond to nature, so much the worse for nature. Nature was irregular, could not be relied upon, but the ideal thing, and Plato was the chief promoter of this doctrine, was that there is astronomy, which consists of perfectly spherical bodies moving in perfect circles. This is real noble astronomy. The actual bodies in the heavens do not quite behave in that way, but they ought to. You can, in fact, study ideal things best, and real things are very poor and distorted images of them. The working out of these distortions came later. For instance, Johannes Kepler, having conceived a rather beautiful idea as to how planets ought to move, actually measured how they did move, and found out that there was only a difference of 8 minutes between the theory and the actual practice, which could easily be neglected. Most people had accepted the theory, but he was particular. He was sure about his measurements, and he said this difference must be real. With that, he discovered that planets did not move in circles. They moved in ellipses. Though, from looking at these ellipses, you could not actually tell that they were not circles. That is how observation, by not fitting, leads to continual improvement of theory. One of the first people that I worked with in physics was Kapitsa. He was a nasty kind of experimental physicist. He never went in much for theory, but he made, or had, of course, all the best theoreticians around him in Cambridge. He would ask them a very simple question. What would be the electrical resistance of such and such a pure metal in such and such a magnetic field? Well, the theory of the conduction of metals in magnetic fields is well known. There is no need to work it out. But when Kapitsa would do the measurement and find that the theory was wrong, well, not seriously wrong, but by a small factor. And then, of course, the mathematician would go back and look at the theoretical calculations, and then would find that he had used approximations, which all mathematical physicists do, that he had neglected terms of higher order, that he had done various things which on careful examination he found he should not have done. He then produced another answer which was now, of course, reasonably in agreement with the experiment. Then Kapitsa would say, well, now, supposing we make the magnetic field 10 times as strong. And here, of course, he was perfectly safe and protected because no one had made a magnetic field as strong as this. So the process was repeated. Thus, the theory is continually refined and criticized and destroyed and reformed by experimentation. If you look at modern physics, which I will not be mentioning in this reading, you will find plenty of examples of this. For instance, with mesons and other new particles where theory has thrown doubt on experiment. And there are plenty of other examples where experiment has proved the theory wrong. Of course, the basis of modern physics is the whole of the quantum theory, which arose out of the limitations of the previous theories of their not fitting the experimental evidence. And so, as we know, we must remember that theory is continually refined and criticized and destroyed and reformed by experiment. Concerning modern physics, I have given you here a very general account, and I only want to say little more in relation to modern physics. I will not be dealing with modern physics for the very practical reason that it is modern and you will not get most of the relevant history of modern physics elsewhere. When I say modern physics, I can be extremely precise. Physics after the year 1896, when the first breakthrough was made, and a most unexpected thing made experimentally and not theoretically in Röntgen's discovery of X-rays. With the discovery of X-rays, the clue came which enabled a number of other anomalies to be cleared up. Let us call the date 1900 for a first approximation, as it is a very convenient date. Modern physics, what is called atomic physics, is quite different from, although it does not contradict, the old physics, as you will see from the study of its history as we go along through time. What I want to do in this series of lectures is to take you up to the year 1900. I remember when I was first an examiner in this university, a rather long time ago in the year 1937. One of the oldest or older examiners said when we were looking at the Bachelor's of Science degree question papers, quote, "There is a question here about the electron. You have no right to ask that question. It is not in the syllabus," end quote. We looked up the syllabus, and sure enough, the electron was not in the syllabus. The syllabus had been made in 1896, and although the electron had been named in the year 1891, it was not, quote-unquote, respectable, and it was therefore not included. Indeed, the kind of physics which existed before all the new discoveries was made in the 20th century was a very complete doctrine, the most complete doctrine imaginable, which is now called essentially descriptive physics. That is, it consisted of the measurement and interpretation of what are called the properties of matter. And for instance, you are told that the specific weight of gold is, you are told the coefficient of expansion of such and such things, you are told the refractive indices, and you are given a certain number of measured constants which manipulated can suitably enable you to discover other things you are going to measure or to predict them. We were told very severely that that was the nature of physics. If you were to ask what things are, you could make an answer, while you could never answer questions of why, or why things happen the way they happen, why things behave the way they do, why the universe is the way it is. For instance, why has water got an anomalous structure? Why does water have a point of minimum density? That is a fact. You learn the fact, and if you learn it well enough and put it into an examination answer, you will get full marks. But that physics consists of knowing the laws. For instance, knowing Boyle's law is good enough for school, but it's not good enough for university. You have to know that you can correct Boyle's law, that you can introduce variables that will improve on Boyle's law and fit the facts better. And the kind of descriptive physics which includes among its laws some which have a rather different status, a better status, like Newton's laws of motion, is the part of physics that covers most of the entire field of modern, or at least classical physics. The exception where you begin to impinge on what I call explanatory physics, and not descriptive physics, is where the atom, or any hypothetical unit, comes into play. It really came into physics to some degree in the 19th century. Curiously enough, it had come into chemistry at the beginning of that century. It was never quite respectable, however, but the atomic theory in chemistry does date back to the year 1804. The atomic theory in physics, however, does not really date back in any full sense earlier than the year 1913 when Bohr's theory of the atom appeared. But I would point out that the concept of the atom was used to explain Boyle's law and the kinetic theory of gases. It was used to a minor extent in electrochemistry, in Faraday's unit of electric charge, which is, as we know now, the electron, but of course was considered to be a hypothetical unit at the time. Now, you do not want to reduce things only to observable constants. You want to reduce the number of observable constants themselves. The object of physics at the present time, it may, of course, again change, is to find the underlying regularities in nature. That is not just to say that gold is yellow and silver is white, but to find out why gold is yellow and why silver is white. We do not know yet. We have no idea. Gold is a fairly complicated atom, and we cannot as yet deduce from first principles why gold should be yellow. We have no reason to doubt that it could be done, and possibly with a good computer, it would be done now. But most of these facts are interesting, not so much in themselves, but just more in what lies below them. For instance, we would very much like to know what metals and what alloys are superconducting at what temperatures. The only way at the present moment to do that is to try to find out experimentally. If we had a proper theory, we could do it mathematically. These then are the generalized tasks of physics. But where there is still an upper physics and a lower physics, I will be talking up only about the lower experimental physics, about things which are detectable and actually measurable. The higher physics, the mathematical physics, still deals with a world abstract that is highly less perfect than Plato would have liked, but nevertheless is for any given time the most perfect explanation of phenomena which you can get. In this first lecture, I have summarized the field, and will deal with it more specifically next time. I think everyone ought to look at least at one original textbook in physics to see what physics was like at any particular time. And one of the nice things to remember is that the further back you go in time, or the history of humans and how they have experimented with the world, the more pleasant physics is to read, because people were more human than in the way in which they wrote about it. In modern physics, I would only mention Dirac's classical book on quantum mechanics. It's not exactly a delight to read, but it is one of the best written of its kind. The older textbooks were written at a time when people did not know as much as we do now, and therefore there was no particular difficulty in our understanding of their content.